let's continue here. Okay. So, right, just go back to our randomized state here. Okay, so let me first explain to you what I'm doing here with the equation for the straight line, because you can see that there's this extra term here that might be a little bit confusing. And why do I multiply x with 10? So if you can see here, it's a full range going from 0 to 10, okay? This range random 50 gives me a population of, or a collection of 50 randomized points between 0 and 1. So I add this extra term here to give me an offset of the same magnitude that you would have on the x-axis, but just a factor 10 smaller. Okay, so if I just draw 2 times x minus 5, I would get an exact straight line there. You know, all of them would lie exactly on top of each other. So this little term here adds the randomized value of x to the value of y. So this gives me a larger distribution around the straight line that they would form. Otherwise, they would all just line smack down in the middle. So this gives me a broader range for the line that I want to fit. So this is more realistic than you would get a straight line. You will never, ever get a perfect straight line out of data that was measured in reality. Simple reason for that is that any measuring device has some form of uncertainty or measuring error on it. You can be the most precise engineer out there, the most precise scientist. You'll always have some uncertainty. So if you repeat a measurement 10 times, there will be 1 or 2 measurements that will have the lost factor of certainty out of whack with the rest. It's a principle of significant figures. I'm not going to go too much into depth about that. That's more physics related, but this extra little randomized term here gives you the randomization scatter there. Okay, so this is the figure that I'm plotting here. X against y. X is our randomized points from 0 to 10, and y is the straight line figure plus then the randomized extra term that I add at the end. So this is our simulated data set. Okay, so forget about that line. This is the case that we actually want to fit to our data. So now we've got this 50 randomized points on our x and y values, and in reality we wouldn't have that equation. So we would just have this collection of points, x and y. Now we're going to use scikit-learn to fit a linear model through our data set. So we've got x and y. X is this random set of 50 points with values between 0 and 10. And y is the value set between minus 5, a little below minus 5 because of that randomized set, randomized value that we add at the end, and it goes all the way up to 15. Okay, so now we want to fit or see if we can actually get the straight line that we fit there. 2 times x minus 5 plus then the extra, well, the randomized factor there will make a little bit of a difference on the minus 5, but it will be close enough to give us an indication of the typical straight line that we would fit through it. Okay, so we give all the values of x to our to the model. We just have we fit the intercept also, so you can have linear just straight lines that fit without an intercept, or others that do. In high dimensional data sets where you have, let's say, 10 or 15 features in your data set that you want to fit a linear model to, you cannot really represent it, well, you can't represent anything that's more than 3-dimensional on an axis system. So sometimes you want to fit the intercept, other times you don't. Okay, so we fit our model through our X data set and then our Y, and then we generate we have a set there of 1,000 points between 0 and 10 that we would use as our well, the linear space is 1,000 points here between 0 and 10. Okay, you guys have seen in space before. And then Y-fit is just getting the actual predicted value from our X-fit. Okay, np.new axis is axis system that we create, a virtual one, dependent on our actual data set that will values that we put into our model. So if we actually fit it through, so X-fit is a linear set of 1,000 points between 0 and 10. Okay, Y-fit is getting the predicted value of the model that was fit by scikit-learn into these 50 points. So it would have a straight line that it would fit through the points. Scikit-learn will try to fit the RMS value. Remember from the last tutorial that we talked about root mean squared. It's the difference between it's the square root of all the sums of the squares. I'll post a link for you guys to give a good explanation for RMS differences, but it's quite a standard measurement or technique to get the best fit of a straight line through these points. Okay, scikit-learn would have a few iterations running through the data set, very standard, and we would actually get our straight line. So this is the predicted straight line from our data set. So this would be similar to a straight line that we would fit out of a randomized set provided to you by a client or for the company that you work. So this is looks quite well, it fits almost in the middle through all of them. Almost half lies above, the other half lies below. So this is quite a good fit. You can go into a much more depth than just fitting using the linear regression routine of scikit-learn. So this is just to demonstrate to you guys the way that we do it. In this plot,